All right, let's get straight into it. Today we're going to crack the code on a full 8-mark question from a higher tier AQA GCSE Physics paper. It's a real test of your knowledge on energy, your calculation skills, and your ability to think like a physicist. So let's dive in. So you see this setup? A toy car, a ramp, and a loop-the-loop. Looks pretty straightforward, right? But getting all 8 marks available here requires some real precision. Our mission is to break this down step by step using the official AQA mark scheme, so you can see exactly how to lock in every single point. Okay, so the first part of the problem, question 8.1, is all about a fundamental concept that really sets the stage for everything else. It's just a single mark, but it's crucial. We need to define what a closed system is.
So, the question is, why can we call the car and the track a closed system? Have a think about what that term really means in physics before we jump to the answer. It's a key idea for the rest of the problem.
And boom, that's it. That's your first mark right there. The key phrase according to the AQA mark scheme is the total energy of the racing track and the car is constant. In a nutshell, that's what a closed system is all about. No energy sneaking in or out.
All right, 1 mark in the bag, 7 more to go. Now let's get into the big one, the 5-mark calculation. This is where we gotta roll up our sleeves and crunch some numbers. Okay, so the question gives us everything we need to start. The mass, the gravitational field strength, and the height. And this is a classic exam trick. Look closely at that height. It's in centimeters. The very first thing you've got to do is convert that 90 centimeters into 0.90 meters. If you don't, all your calculations from here on will be off. It's a super common place to lose a mark, so always check your units.
So how do we figure out the car's speed down at the bottom of the ramp? Well, first, we have to know how much energy it's starting with. Since it's being held up high, all that energy is stored as gravitational potential energy, or EP for short. And here's exactly how we do it. The formula for EP is pretty simple. It's just mass times g times height. So we just plug in the numbers we have, 0.040 for the mass, 9.8 for g, and crucially, our converted height of 0.90 meters.
You pop that into your calculator, and you get 0.3528 joules. And get this, just writing that down correctly gets you a mark, according to the official scheme. So that's our starting pot of energy, all ready to be turned into speed.
Now this is where the magic happens. Remember that closed system thing we talked about? Well, this is why it matters. All of that potential energy the car had at the top doesn't just disappear. It gets converted into kinetic energy, the energy of movement, by the time it reaches the bottom. So that 0.3528 joules of EP, well, that's now our EK.
So we know the kinetic energy, but how do we get the speed out of that? Let's break it down. First, we take our energy value and set it equal to the kinetic energy formula, which is a half mv squared. Then we slot in the mass. The next bit is just a little algebra. We need to rearrange the whole thing to get v squared on its own. And for the final step, to get v, we just take the square root. If you show these steps clearly, you're picking up marks all the way through.
And there you have it. The final answer is 4.2 meters per second. That's it. That's the full 5 marks for this calculation, all from carefully applying that one big idea, the conservation of energy.
Awesome. So we've banked 6 out of the 8 marks available. We're on the home stretch now. This last part isn't so much about crunching numbers. It's more about thinking like a physicist.
Okay, here's the final puzzle. To get to the very top of the loop, position C, the car needs to gain 0.20 joules of potential energy. So the big question is, how much kinetic energy does it need at the bottom of the loop, at position B, to actually make it all the way around? Does it need less than 0.20 joules, exactly 0.20 joules, or more?
The correct answer is more than 0.20 joule. But hold on, just ticking that box only gets you 1 of the 2 marks here. The really important part, the part that gets you the second mark, is explaining why.
And what's cool is that the AQA mark scheme actually gives you a few different ways to get this right. Here's the main idea. Think about it. If the car had exactly 0.20 joules of kinetic energy at the bottom, it would use up every last bit of that energy just to reach the top of the loop. It would just stop and fall straight back down. To actually complete the loop, it has to still be moving when it's at the top, right? That means it needs some leftover kinetic energy. You could also get the mark by talking about the real world, pointing out that some energy is always going to be lost to things like friction or air resistance.
And that is how you get all 8 marks. We've tackled the definition, a big calculation, and a tricky reasoning question.
But if you take a step back, what's the one single idea that ties this entire problem together?
It all comes down to one of the most fundamental rules in all of physics, the conservation of energy. That's it. It's the reason we could say that total energy was constant in our closed system. It's the principle that let us turn potential energy into kinetic energy, and it's the key to understanding why we needed that little bit of extra energy to make it over the loop. Master that one powerful idea, and you've cracked the code to this entire question.